Hello, so this is our next lecture section on resampling statistics. This section here will provide another example or two of randomization approaches. We've seen one in a previous screencast. So in example number 2, we have a one-way between subjects design, and there are 4 groups, arbitrarily labeled 1, 2, 3, and 4. So if it were a parametric analysis we were going to do, it would be an independent group's ANOVA. So we might look for a non-parametric approach when we weren't happy that the data here were satisfactory for parametric analysis, either very small samples or their assumptions underlying the parametric test, the ANOVA, were likely to be violated and jeopardize the p-values we would get. This isn't probably true, so there's a problem here for this set of data, but we're just going to use them as illustrative data for this approach. Here are the 4 groups, and there are 4 groups of 11 subjects, same number in each group, and there are their scores on some variable. And so we just lay it out in a long, thin format, DV and group code 1, so on, all the way down to the last subject, the 44th subject, scoring 14 in group 4. So the question is, as we've discussed before, how by randomization can we remove any real effect that might be present, that might be differentiating the scores for one group from the others, or group differences in those scores in more generally. So we can just randomize without replacement as before, but we do it by randomizing the group labels against the scores. So we mix up any association randomly that might exist in the real data between the score and the group label. We randomly mix away that pattern, if there is one, linking group code to scores. So in each resample, you just randomize without replacement, randomizing away that pattern, and we're going to calculate a statistic for each resampled sample, and we're going to test the actual statistic from our real data against the sampling distribution, the resampling distribution of our statistic. And so the final question is, what statistic might we use? We'll come on to that later. Here are the 2 programs that are available, essentially identical. One written for Statistics 101, ANOVA randomization.txt, and a slightly more detailed program in terms of at least the outputs, the printout and how it looks on the screen, ANOVA randomization.m, the Matlab code. So there are the summary data. Actually, as I said, doesn't look that problematic for parametric statistics, and the sample isn't tiny, 11 in each group. Power might, of course, not be very high. So, but we're going to use it, as I said, as an illustrative example. There are the means in each of the 4 groups, and this is the grand mean for all the groups, which actually equals the mean for the 4th group by chance. So we could use the F statistic that we use in analysis of variance, and just treat it as if its sampling distribution might not be an exact F distribution. But rather than go to all that trouble, we can compute a pretty equivalent statistic. Here we're going to call it the sum squared deviation of the means. That's the difference between each mean, group mean, and the grand mean squared. And we see it's been calculated here, and we get a value of 1.7 approximately for this sample. So now we've done our randomization as before, mixing up the links. And this is the sampling distribution of that sum squared deviation statistic that we get under the null hypothesis, because the randomization ensures that the null hypothesis is true across the resamples. And what we can see is the value from the experiment, 1.7, lies somewhere here, well in the middle of the distribution. At least 60% by eye looks to have as large or a larger value than the value actually in the data. So you have no confidence in rejecting the null hypothesis, which is in keeping with the pattern you saw earlier in the bar chart. And the critical value would be somewhere around here, much, much higher. So only if the value in our experiment was up this end would we above 7-ish, we would be unlikely to accept that it generated from a sample that was true under the null hypothesis. The p-value would be less than 0.05. And that's the end of randomization example number 2.